Welcome to Iron Process, where engineering is no longer defined only by scale, but by the ability to organize materials, machines, and human coordination into systems capable of operating under extreme conditions. From massive concrete pours deep within mountainous terrain to subsea tunnels driven beneath heavily populated urban corridors, modern infrastructure is built through processes where precision, sequencing, and control determine long-term performance. This is where construction moves beyond conventional limits. Let's explore how large-scale engineering systems are transformed from design into operational reality. Construction of the Yusufeli Dam officially began on December 21, 2012, representing one of the most ambitious hydropower developments undertaken in Turkey during the 21st century. The project was developed and managed by the General Directorate of State Hydraulic Works, DSI, as part of a long-term national strategy focused on water resource management and sustainable energy generation. The Yusufeli Dam was designed as a double-curvature concrete arch structure, reaching a final height of 275 meters, placing it among the tallest arch dams ever constructed worldwide. Once completed, the reservoir achieved a storage capacity of approximately 2.2 billion cubic meters, allowing regulation of the Kora River while significantly improving hydroelectric generation efficiency throughout the region. To construct a structure of this scale, more than 2.9 million cubic meters of concrete had to be placed under tightly controlled quality management procedures. Each concrete block was poured according to a highly coordinated sequence to maintain structural continuity across the dam body. This was not simply large-scale concrete placement. It was thermal and structural control at massive volume. The concrete mix itself was specially engineered to withstand extreme compressive forces, while simultaneously reducing heat generated during hydration. Without this control, temperature differentials inside the structure could create internal cracking capable of compromising long-term durability. The project was executed by a consortium of leading Turkish contractors, including Limak Construction, together with several major industry partners. Operating inside the rugged mountainous terrain of Artvin province, introduced major logistical and geological challenges throughout every construction phase. Foundation preparation became one of the most critical operations of the entire project. Engineers carried out deep excavation works, controlled blasting sequences, and multi-layer stabilization systems to prepare a rock foundation capable of resisting enormous hydrostatic pressures once the reservoir became operational. The structural concept of the double curvature arch played a key role in the project's efficiency. Instead of allowing water pressure to act directly across the entire dam body, the geometry transfers loads laterally toward the abutments on both sides of the valley. This significantly reduces direct structural stress while improving long-term stability. Inside the dam structure, an internal cooling pipe network was installed to regulate concrete temperature during curing. For large volume pours, this cooling system was essential. Without thermal regulation, the curing process could generate internal stresses large enough to damage the structure before completion. At the same time, diversion tunnels were excavated to redirect river flow away from the construction zone. Maintaining dry working conditions inside the valley was necessary to sustain continuous operations throughout the build. Supporting infrastructure also became a major part of the project. Access roads, transportation corridors, and regional connectivity systems were developed under DSI coordination to support equipment movement and long-term operation of the facility. The completed hydropower plant achieved an installed generating capacity of 540 megawatts, with an average annual output of approximately 1.88 billion kilowatt-hours. Deep underground caverns house the turbines and generators. These systems are connected through high-pressure penstocks that channel water efficiently into the power generation system to maximize output. As reservoir impoundment progressed, the valley gradually transformed. What had once been a fast-moving river evolved into a massive reservoir system that now provides both economic value and a significant environmental presence across the region. The Yusufeli Dam represents more than a hydroelectric facility. It demonstrates how structural engineering, geological management, logistics, and energy infrastructure can be integrated into a single coordinated construction system. It reflects the combination of strategic planning, modern technology, and sustained human execution required to harness natural resources for long-term national development. Far from Turkey, along the rugged terrain surrounding the Indus River, another massive hydropower system is taking shape. The Dasu hydropower project is developing into one of the largest and most highly organized infrastructure construction sites in the region. Diversion tunnels are driven directly through mountainous terrain to redirect river flow away from the primary construction area. This allows excavation and structural works to proceed under controlled conditions. Across the site, heavy machinery continuously removes enormous volumes of rock, while the cofferdam system stabilizes river behavior during construction operations. The project is managed by the Water and Power Development Authority, WAPDA, together with international contractors, primarily from China, including China Gajoba Group. Dasu is being constructed in two separate development phases. Each phase delivers approximately 2,160 megawatts of capacity, bringing the total installed generating output to roughly 4,320 megawatts once completed. The project is expected to significantly reduce Pakistan's long-standing electricity shortages while strengthening long-term energy reliability. In a completely different environment, deep inside the Rocky Mountains of Norway, underground transportation infrastructure is being executed with equally demanding technical standards. Tunnel systems are excavated using drill and blast construction methods before being reinforced to maintain structural stability under highly variable geological conditions. These projects are overseen by the Norwegian Public Roads Administration, Statens Vegvesen, with the objective of improving transportation connectivity while ensuring safe operation in severe environmental conditions. Once completed, these tunnel systems reduce travel time while minimizing the impact of weather and terrain across mountainous routes. Although projects like Yusufeli, Dasu, and the Norwegian tunnel systems exist within entirely different environments, they share a common principle. Large-scale infrastructure depends on organization, sequencing, and continuous control. Every operation from excavation and stabilization to concrete placement and system integration contributes directly to long-term performance, operational reliability, and sustainable infrastructure development. At the Back River Wastewater Treatment Plant site in Baltimore, USA, construction methods are shifting away from traditional labor-intensive reinforcement installation toward a more controlled assembly-based process. Instead of tying reinforced concrete walls entirely in place, large reinforcement cages are prefabricated at ground level before being lifted into position as complete structural assemblies. These massive steel cages are hoisted and lowered with millimeter-level precision to align directly with the starter bars extending from the foundation system. Every movement during lifting operations must remain perfectly coordinated. Even minor misalignment during placement can interrupt the entire workflow and compromise connection accuracy. At the center of this system is the HRC 500 series mechanical coupler technology. Rather than relying on conventional lap splices, reinforcing bars are connected directly using threaded couplers that create a continuous structural load path throughout the assembly. Installation begins by rotating the coupler into position so the threaded sections engage correctly. Specialized tightening equipment is then used to apply the required torque and secure the connection. For large diameter reinforcement bars, such as number 14 bars measuring approximately 43 millimeters, precision throughout every stage becomes essential to maintain structural integrity. This approach introduces several operational advantages. Installation time is significantly reduced because entire reinforcement assemblies can be prepared in advance instead of being tied piece by piece at elevation. Steel congestion around splice locations is also minimized. This allows concrete to flow and consolidate more effectively during placement, reducing defects such as voids and honeycombing. Eliminating traditional lap splices further improves material efficiency while enhancing overall structural performance. Safety also improves substantially. Because most reinforcement work is completed at ground level, the amount of work performed at height is greatly reduced, lowering operational risk throughout the project. What appears to be a relatively small procedural adjustment ultimately transforms the entire construction workflow. More broadly, the Back River project demonstrates a wider transition occurring across the construction industry. Execution is moving away from labor-heavy installation methods toward precision-controlled assembly systems. Construction is no longer driven only by field experience. It is increasingly directed through engineered processes, specialized equipment, and tightly managed sequencing. The lesson becomes clear. In modern construction, speed is not achieved by forcing individual operations to move faster. It is achieved by restructuring the entire system intelligently. When engineering, workforce coordination, and equipment integration operate together, projects can be delivered more efficiently while also achieving higher long-term structural reliability. On October 12, 2016, the first concrete pours for the Sabia Beach project were placed into the foundation system, marking a major milestone for the entire development. Long-term structural stability depends heavily on this stage because foundation quality directly determines the performance of all systems built above it. Before concrete placement began, the reinforcement network had already been fully installed according to the structural design drawings. Large diameter reinforcing bars were densely arranged and securely tied together to create an integrated load-bearing framework. Every intersection underwent detailed inspection to ensure proper load transfer capability, while minimizing the risk of future cracking or deformation during service life. Concrete supply operations on-site were organized with strict continuity. A fleet of Cemex transit mixers operated within a closed delivery cycle to maintain uninterrupted concrete supply during the large foundation pours. Continuous placement was critical. Interruptions during massive pours can weaken bonding between layers and compromise structural consistency. To place concrete inside confined basement areas where direct access was limited, a swing boom pump with extended reach capability was deployed. At the placement zone itself, crews worked in close coordination throughout the operation. Concrete discharged steadily from the pump, while workers simultaneously operated internal vibrators to remove entrapped air from the mix. This consolidation process was essential. Proper vibration prevents honeycombing, improves bonding between reinforcement and concrete, and ensures long-term structural performance. quality control procedures remained active throughout the pour. Concrete slump values, typically ranging from 12 to 18 centimeters depending on mix requirements, were tested upon arrival to verify workability. Samples from each batch were also collected and cast into standard test cylinders. These specimens were later tested for compressive strength at both 7-day and 2-8-day intervals, two of the most important indicators of concrete performance. Once placement was complete, the slab surface was finished, using mechanical power trowels to achieve the specified elevation and flatness required for subsequent construction stages. The successful completion of the first pour represented more than the beginning of physical construction. It demonstrated how technical control, workforce coordination, and process management must operate together from the very first stage of the project. The principle is fundamental. Structural quality is not created at the finishing stage. It is established at the foundation, where every detail influences long-term durability. In Istanbul, another infrastructure system pushed engineering requirements even further. Beneath the Bosphorus Strait, which separates Europe and Asia, an undersea tunnel was constructed to create a direct transportation link between the two continents. The Eurasia Tunnel extends approximately 14.6 kilometers in total length. On the European side, existing road systems were expanded and reorganized using interchanges, overpasses, and pedestrian connections integrated directly into the surrounding urban infrastructure. This allowed traffic flow to remain continuous before vehicles entered the tunnel itself. Deep beneath the Bosphorus, excavation was carried out using one of the largest tunnel boring machines ever deployed, operating with a shield diameter of approximately 13.7 meters. The machine advanced under water pressures, reaching up to 11 bars, while passing through highly complex geological formations. Average excavation rates ranged between 8 and 10 meters per day. Every stage demanded strict operational control to maintain both safety and structural stability. The tunnel itself was designed as a double-deck structure containing 2 traffic lanes on each level dedicated to light vehicles. This configuration maximizes traffic capacity while maintaining efficient movement through the system. Ventilation, monitoring, and safety infrastructure were fully integrated into the tunnel network, allowing continuous 2-4-hour operation with high operational reliability. On the Asian side, approximately 3.8 kilometers of additional roadway directly connected the tunnel to the existing highway network. Transition zones between systems were carefully engineered to maintain smooth vehicle movement throughout the route. Once operational, the tunnel reduced travel time between both sides of Istanbul from more than 100 minutes during heavy congestion to roughly 15 minutes. The impact extends beyond convenience. Reduced travel times improve urban efficiency while lowering pressure on existing transportation corridors. The Eurasia Tunnel demonstrates that the value of modern infrastructure is not defined by a single technical record. Its value lies in how multiple engineering systems are integrated into a stable, efficient transportation network. From high-pressure tunneling technology and double-deck structural design to fully integrated roadway systems at both ends, every component was developed to support long-term sustainable mobility. The project also demonstrates a broader engineering reality. Natural barriers are no longer absolute limitations. With sufficient planning, technical capability, and system-level coordination, geography itself can be restructured through infrastructure. The Eurasia Tunnel does more than connect two continents. It shows how engineered systems can directly influence mobility, efficiency, and quality of life within a modern city. On bridge erection projects, the lifting and placement of concrete girders remains one of the most demanding operations in structural construction. These operations require strict coordination, precise calculations, and continuous control throughout every stage of installation. Large girders weighing nearly 200 metric tons are commonly installed using crawler hydraulic cranes with lifting capacities ranging from 400 to 500 metric tons. Even with equipment of this scale, every lift must remain within carefully controlled operating limits. Before lifting begins, engineers calculate working radius, boom angle, and suspended load to ensure the crane remains within its approved load chart. For lighter girders weighing approximately 80 metric tons, tandem lifting systems using 250 metric ton cranes are often used. In these operations, synchronization becomes critical. Both cranes must move together with perfectly controlled speed and direction to prevent torsion, imbalance, or structural misalignment. As the girder approaches its final position, hydraulic systems allow fine adjustment down to individual centimeters. Signal workers and crane operators coordinate continuously to guide the girder accurately onto its bearings. Immediately after placement, engineers verify alignment, elevation, and bearing contact conditions before final fixation begins. The process demonstrates more than the capability of heavy lifting equipment. It reflects the integration of engineering calculations, operational discipline, and field coordination into a single controlled construction system. In November 2018, at the Gamuda Gardens Township project in Rawang, Malaysia, precast concrete girder installation became a major stage in completing the overpass system and internal road network. The process began with transporting large I-beams from the casting yard to the site, using multi-axle trailers designed to distribute loads evenly during movement. Before erection operations started, engineers inspected rigging systems, lifting loads, and crane operating conditions to minimize construction risk. At the site, large mobile cranes lifted the girders onto a launching girder system positioned above the bridge piers. From there, the girders advanced across the span through the steel launching framework. As each girder neared its final location, workers positioned at the pier tops carried out alignment adjustments with centimeter-level precision to ensure proper seating on the bearings and compliance with design elevation. After installation, additional checks were performed to verify stability and structural safety before the next construction stage proceeded. The successful completion of girder installation not only maintained project progress, but also created durable bridge spans, capable of improving long-term transportation connectivity. On August 17, 2013, the Hardanger Bridge officially opened to traffic after 4 years of construction, becoming one of the world's longest suspension bridges with a main span of 1,310 meters. The project represents a highly optimized approach to modern suspension bridge construction. One of the most important engineering decisions involved the approach alignment. Instead of expanding roads directly along the fjord shoreline, where terrain conditions were unstable and construction risks remained high, engineers selected tunnel connections at both Vallavik and Boo. This solution minimized large-scale surface excavation while utilizing stable rock formations inside the mountainous terrain. The bridge towers, each approximately 200 and 2.5 meters high, were constructed using self-climbing formwork systems that allowed precise control over geometry and concrete quality during every casting stage. In suspension bridges, tower geometry directly controls the geometry of the entire cable system. Because of this, deformation and vertical alignment had to remain tightly controlled throughout construction. The main cables were installed using aerial spinning techniques. Tens of thousands of galvanized steel wires were spun continuously between the towers before being compacted into two massive structural cables with extremely high load capacity. Executing these operations under strong wind conditions inside the open fjord environment required advanced construction management and strict safety control. The bridge deck itself consists of steel box girders fabricated off-site and transported to the project location by sea. Each segment weighing hundreds of metric tons was then lifted and suspended directly from the cable system. This installation method minimized work at height while improving assembly precision and construction efficiency. The total installed steel weight reached approximately 7,850 metric tons. During the final construction stage, the main cables were compacted, sealed, and equipped with an internal dehumidification system designed to reduce moisture and prevent internal corrosion over the long term. Additional systems, including hangers, railings, and auxiliary components, were installed through integrated construction procedures developed for harsh environmental operation. Overall, the Hardanger Bridge reflects a clear engineering philosophy: optimize structural systems, maintain strict construction control, and prioritize durability throughout the entire service life of the structure. Another example of controlled infrastructure construction can be seen in diaphragm wall systems. Diaphragm wall construction generally consists of four primary stages: excavation, reinforcement cage, installation, stop, end placement, and concrete casting. This deep foundation system is widely used in underground projects where stability and water tightness are critical requirements. Excavation is carried out using hydraulic grabs operating inside predefined trench panels. During excavation, bentonite slurry is continuously maintained to stabilize trench walls and balance surrounding soil and groundwater pressures. Once excavation reaches the required depth, the trench base is inspected and cleaned with sediment thickness, carefully controlled to maintain concrete quality. Next, prefabricated reinforcement cages are lowered into position using cranes, while alignment and verticality remain under strict control. Spacers are installed to maintain concrete cover thicknesses ranging from 70 to 100 millimeters, improving durability and structural performance. Stop-end panels are then installed between adjacent trench sections to maintain continuity and water tightness throughout the wall system. Concrete placement follows using tremie pipes in a bottom-up casting process. During pouring, the tremie pipe tip must remain embedded inside the concrete to prevent contamination from bentonite slurry and avoid segregation. The pour continues without interruption to maintain structural uniformity across the entire panel. Once completed, the panels form a continuous diaphragm wall system, capable of providing both structural support and groundwater cutoff performance. The entire process depends on coordinated control across every stage. Even relatively small deviations during excavation or casting can directly affect long-term structural quality. In modern infrastructure construction, performance is no longer measured only by speed. Efficiency and sustainability have become equally important. One example is in-place pavement recycling. The process begins by spreading aggregate with controlled thickness, while carefully managing moisture and material gradation to maintain bonding performance and base stability. The core stage uses a Wirtgen 2000 200 CR recycling machine, which mills existing pavement layers before crushing and mixing the material in situ with stabilizing agents to create a new structural base layer. After recycling, compaction operations are performed to achieve the required load-bearing density. During finishing operations, a Weiler material transfer vehicle works together with a Vogela paver to maintain continuous asphalt placement, while controlling paving temperature to reduce segregation and improve adhesion. The main value of this process lies in material reuse. By recycling pavement directly in place, emissions and material consumption are reduced, while construction efficiency improves significantly. Track laying for the Ruijin to Meizhou Railway was carried out using the specialized PG-28 track laying machine as the project advanced into the superstructure phase. The railway extends approximately 240.29 kilometers, with bridges and tunnels accounting for nearly 73.86% of the total route. Because the line passes through mountainous terrain and variable geological conditions, construction required extremely precise control throughout every stage. Mechanized installation systems maintain consistent track geometry, including elevation, alignment, and gauge, ensuring long-term operational stability and safety. Upon completion, the railway will connect 3 counties to the national rail network for the first time, reducing regional development disparities and improving transportation connectivity. At industrial facilities such as the Lehigh-Hanson plant, reinforced concrete silos remain essential for maintaining continuous production operations. Over time, exposure to harsh environmental conditions together with internal loading can create cracking, moisture intrusion, and reduced structural capacity. One of the primary structural challenges comes from circumferential tensile stresses generated by stored materials pressing outward against the silo walls. To strengthen the structure, rhino carbon fiber reinforced polymer systems were applied. The process begins with surface preparation and epoxy crack repair before carbon fiber sheets are wrapped around the silo circumference and bonded using specialized epoxy resins. With extremely high tensile strength and strong corrosion resistance, the CFRP system acts as an external reinforcement layer that improves hoop strength while limiting crack propagation. Depending on structural requirements, multiple reinforcement layers can be installed to optimize performance while minimizing operational interruption. As a result, structural deficiencies can be mitigated while significantly extending the service life of the facility. Across projects ranging from hydropower dams and subsea tunnels to bridge systems, diaphragm walls, railway infrastructure, and structural strengthening technologies, one principle continues to emerge. Modern construction is fundamentally about system control. Technology is no longer only supporting construction activity. It is reshaping how infrastructure itself is organized, executed, and maintained. From mechanized tunneling and thermal regulation systems to mechanical couplers and advanced composite materials, every development is focused on reducing variability, improving consistency, and increasing long-term reliability. At the same time, the boundary between design and construction continues to disappear. Engineering solutions are now developed together with construction methodology, geological analysis, and operational requirements as part of a fully integrated system. Human expertise remains essential, but execution no longer depends solely on individual experience. It now operates within tightly controlled systems supported by equipment, standards, monitoring technologies, and data-driven management. This integration reduces risk, improves safety, and maintains quality even under extremely demanding construction conditions. Ultimately, the true value of modern infrastructure is no longer defined only by scale. It is defined by how effectively engineering systems are integrated into structures capable of maintaining durability, efficiency, and long-term operational performance. At that level, infrastructure becomes more than physical construction. It becomes part of a larger system supporting mobility, industry, energy, and sustainable development for future generations. Thank you for following IRON Process. See you in the next system.